Hello, everyone. Welcome back from the brief break. Our next speaker is Brett Slatkin. Brett is the author of Effective Python. He is a principal engineer at Google, where he's written Python professionally for 20 years. And Brett, take it away with the future of Python, evolution or succession.
Great, thanks. Can everybody hear me okay? All right, sweet. Okay, so today we're going to talk about the future of Python. I wanted to represent this with a tapestry, a medieval tapestry, because I feel like this is a momentous occasion where history is being written. I don't know what the outcome will be, but I think we'll be talking about it for a long time. There's a choice that's going to happen, or some kind of outcome is going to happen, that Python is going to have a future, but the question is it going to evolve to become the language that everybody needs right now, that's emerging, or is it there going to be a succession where there's some other language that actually takes the ecosystem away from us and away from Python? I think those are the two choices that we're facing, and this is a grand tale. So I'm going to talk about that today. So give you some framing, past, present, and future, and then kind of the existential crisis that we're facing here. In terms of the framing, there was this really amazing poster back in 2003 that O'Reilly, the book publisher, put out. I don't know if you've seen this before, but it's like the ancestry of all the programming languages in the world at that time. Programming languages have been around for about 50 years. It's a really cool poster. And it all starts with Fortran in 1954 and Lisp in 1958 as kind of the two roots of the whole family tree, arguably. And then Python is here in 1991. And what's cool about this chart is it shows kind of like how there's cross-pollination between the different languages and ideas kind of went between them, and how there's also kind of languages evolved or had some kind of lineage. A great example of that, if we zoom in on C, C actually started with CPL, and then that became BCPL, which then became B, which then became C. And that's all derived from A, algol, right? So it's just very kind of interesting past. Another view, this is probably a more common one you've seen, is the TOB index of popularity of languages. This is basically how often are people using them. You can go to their website to find out about the methodology. I'm not going to talk about that now, but Python, here's Python. Back in 2003 when that poster was made, Python was like 1%, way down on the list of languages. And now Python is the number one with 21%. C back in when Python was 1% was at 18% in second place, and now C is also in second place, but now with 11%, which is kind of wild. But what both of these charts don't show is what happened to the user groups, like how the users went between the languages. And I think that's the really important thing that we're going to be talking about today. We've seen migrations of users many times in the past. So here are a bunch of examples. So this is not about the ancestry of the language or the paradigm of the language, and it's not about the popularity of the language. It's more about like where did the users go? So let's take the first line. You're an Apple user writing BASIC on an Apple IIe, and then after that they're like, hey, use Toolbox with Pascal, and then actually no, you can use C for that. Hey, now we've bought Next, and you're going to use Objective-C to write on macOS 10. Hey, actually, Swift is better, use that instead. So if you're in the Apple's ecosystem, you've kind of moved between these languages because that's where the ecosystem went, that's where the user community went. So it's a migration between these. We've seen this in browsers, between JavaScript and TypeScript becoming really popular, and now at WebAssembly, and on and on. Another very famous example is Perl became PHP with web development, and then Ruby on Rails just blew everything open. I mean, it was wild. And now Node is here, which is kind of like taking that back. So it's just been interesting what's happened. So there's some real fundamental questions here. So we know that languages evolve and the user groups move. And if you look back at that chart, languages seem to last like 10 to 25 years before there's some kind of succession. Either the language evolves like C into C++, or the language dies. And Python is 35 years old. So we're kind of overdue. And so the question is how do we get here and where are we going next? And so that's what I'm going to try to talk about. All right, so looking at the past, you might have heard this before. Guido has this blog post. There's a link here at the bottom, and the slides I'll share a link to later if you want to go check out the details. He talks about this language called ABC, which is like a teaching language and a research language. He says that these are all quotes from Guido, that's the primary influence was ABC. It was meant to teach people how to program and replace BASIC. It used indentation just like Python does, so that's where they borrowed it. And the other thing was they did a bunch of user testing, and users couldn't understand the indentation until they added the colon, which kind of drew the eye to kind of something was coming. And so they actually did user testing, which is really interesting in order to develop the language for understandability. He also says a lot of the data structures came out of that language. And if you look at ABC, so here's some ABC code. This is from like a Colossal Cave Adventure kind of game, like a text-based game. You have an inventory of items that you're carrying as you explore a cave, and so this just prints out what you're holding. But you can see it defines like 2 subroutines using indentation. There's some kind of like match case syntax in here, which is wild because this is 30 years before Python got it. And so yeah, and feels very Pythonic in some ways. So that's a big influence on Python's ancestry as a programming language, like the actual construction of it and logic of it. It also has Unix as a big ancestor. So C had just been ratified in '89, the C89 standard. There's all these Unix scripting tools out there, Perl and Tickle. These are really popular tools. And the idea in Unix was just like, let's glue a bunch of tools together and make them work. So scripting was just kind of in the air when Python was being developed. And so that was another big kind of part of the ancestry of the language development. Then there's this question of where did the users themselves come from? And so scripting was a big one, like we just talked about. The other 3 are Lisp, Fortran, MATLAB, kind of science, and then S and R, which are kind of statistical mathematical communities. I'm just going to go through some of these. So with Lisp, there's this guy named Peter Norvig. He's pretty famous. He wrote the book on building AI systems with Lisp. This is like an amazing tome. They ratified Common Lisp in 1992, like when this book was published. So he was like on top of the world. Huge amount of funding for AI with Lisp. The bottom dropped out of that, which was interesting. And so in 2000, he wrote this blog post, which is like Python for Lisp programmers. And he basically says that Python is a Lisp dialect. So you have the guy who wrote the book on Lisp being like, Python's Lisp. And that's interesting. And he says, it does everything Lisp does. It doesn't have macros, but you can use eval, so it's good enough. And he has tons of really cool example code of using Python to do kind of Lispy things. So people looking for influence and watching the Lisp community kind of dying because of a lack of funding, and that's a different talk another time, they're like, wow, let's try out Python. Then Paul Graham, who you might know from Y Combinator, who's invested in most of the startups that we use, companies we use all the time. He had a book called On Lisp. He was a huge Lisp aficionado as well. He actually gave the keynote at PyCon in 2003. And this is before I even knew how to write Python. I don't know if anyone in this room was at that PyCon. Brett, good? I figured. So he talks about the 100-year language and the requirements for 100-year language. And he says, open source languages like Python are really exciting. He makes some predictions, wondering like, what is it going to be like to write programs in 100 years? Do we just tell computers what to do? It's kind of an amazing moment now to look at this, right? But his belief was that we're still going to tell computers what to do and recognize what we're saying to them as programs, as opposed to human text. It's like it's still going to be a program. So that's Paul's line in the sand. The other community here is the kind of Fortran MATLAB crowd. This is a lot of the kind of like academic researchers who worked on like physics and astronomy and stuff like that. Fortran was really fast but kind of annoying to use. MATLAB was like a proprietary version that was easier to use but cost money. It was in a lot of universities, but you can see that like at some point Python took off in traction, and so this is like a graph of astronomy research papers that use Python instead of IDL, which is a type of Fortran. So you can see Python just like took off in the community, and that's where a lot of Python users came from. Another big one is S, which is a precursor. It's like a proprietary precursor to R, which you might have heard of. And then R is essentially pandas, if you've used the pandas library in Python, data frames. There's also a T, but that's a Lisp. We can talk about it another time. But the point here is that the Python community built these amazing packages, NumPy, pandas, Jupyter Notebooks, Matplotlib, stat models, and SciPy. Over time got enough capabilities that there was just no reason not to be using Python for these things. And part of what, if you look into this, it's like, Python was really good at gluing stuff together. As part of your research paper, you had to like copy some files and do some chugging through some data and use some random tool and some lab stuff. And like Python could do all of that because of its scripting abilities. So when you added in the scientific kind of mathematical capabilities on top of that, it just became a no-brainer. So that's where a lot of the users came from. So now let's talk about kind of where we are right at this moment. So Python has some really big limitations. I think I'm not going to complain or dwell on these, and I'm not trying to like criticize. It just is what it is. We've got straight line performance issues. We're not the fastest language. We're not very good at parallel computation across cores. The type system is kind of optional, and it doesn't really always give you what you want out of it. And there's no way to actually extend the language in a kind of generic programming way. So for example, if you look at data classes, the way they're implemented, it's just actually evaluing and execing code under the covers, believe it or not. There's no kind of templating or syntactic macro system. We're going to go through these real quick. So in terms of speed, huge amount of progress on Python speed and performance. You can see that we've basically, since Python 2.7, which is the last yellow bar, we've doubled in speed. And this is thanks to a lot of work from sponsors of this conference, open source community, core developers, really amazing. And so, and JITting has helped here and all kinds of other cool things. Lots of room, lots of like juice to squeeze from this, which is great. But if you compare Python to other languages, this is the old benchmarks game that you might have heard of. It's a geometric mean across a lot of different benchmarks. You can see C here is down like 1, the fastest one. Here's a bunch of other languages where they stack up. You note that the scale on the left is log scale, so it's exponentially slower the higher up you get. And so here's Python. It's like 75 to 100 times slower than C. And that's even the fast version of Python, right? And so, Python's still pretty slow, in a straight line. If you add accelerators into this, like GPUs and TPUs, it's like 1,000,000 times slower than what you can do with C. So it's like a lot slower getting things done. But the community's also done a lot, like I said. And so with the packages out there, like NumPy, you can see that NumPy has taken many operations that were really slow in Python, taking like fractions of a second, like almost 100 milliseconds, down to less than a millisecond, so 1,000 times. So if you're using NumPy or Pandas or one of these other libraries, you're getting some really good performance out of Python, which is great. And so the community has responded. Same thing with Cython and Numba. These are tools like Cython is a tool to let you basically write C code using Python, and Numba is a dialect of Python that lets you massively parallelize it automatically, which is super cool. You can see that the orange line, it's a linear speed up over Python, so that the lines are parallel, so it's faster, but it still doesn't scale in parallel, where Numba is just a flat graph because it's maximizing the usage of cores. So there are options that we have in the community to go faster, which is great, but C would still be like at the bottom of the line. There's also been some work here on making Python more parallel. Free threading is now built in, some experiments. There's multiprocessing that's been around for a while. Threading itself does I/O. There's a great talk by Lisa Roach from PyBay last year where she goes into how this works and all the different things. I totally recommend you check that out. There's a URL there. And you can get some serious performance out of Python now for parallelization, which is great. So we have these limitations. We're making progress on performance, which I'm really happy to see. There's also a bunch of alternative runtimes that have come around to try to make Python even faster. Cinder is one of them that Meta has used for Instagram, which is like the most successful Python app, I think, in history, right? And there's other startups like Mojo working on this. There's the Spy project from Anaconda that's trying to do something here. There's also some other projects that are dead or newly zombied, which is unfortunate, but there's a lot of people who have tried to make Python faster because it's so important to make it more broadly useful. Now we're talking about the last two problems that are out there. One of them is the type system. So the type system doesn't really the type system doesn't make Python any faster. It's there for error detection and linting, but it doesn't really make it faster. In other languages, when you give it types, your code goes faster because it knows how to vectorize and optimize and use SIMD functions and stuff like that. So Cython lets you kind of sprinkle in a bunch of typing information. And if you do this, suddenly it just gets 1,000 times faster. It's I can put that in an integer, and that can be in a register on a CPU, and that can go super fast. And so it'd be great if this was just built into Python, or if the Python type system just did this for you. Wouldn't that be great? MyPyC and some other tools kind of get there, but it's not really part of the standard. There's also just expressivity problems. If you've ever looked at a modern machine learning model or data flow data pipeline in Python, you'll see all kinds of weird smells. I'm going to just blow through this really fast. Apache Beam is like a MapReduce Spark-like system for doing kind of computations and MapReduce shuffle and all that stuff. And it uses these pipe operators and shift operators. This is Python, but I don't know what it means. You have to know the dialect. And so there's this impedance mismatch between Python and what this is. Like, I understand what they're trying to do. I'm not saying it's a bad choice, but I wish there was a better option, and there isn't yet. Similarly, JAX, which is a library for differentiable Python, which is used for most of like, a lot of machine learning models and generative AI models. Don't even try to read this, but like every single line is accessing the library. You're just like, access this, use this module function. There's no like native Python code. You're basically just doing like CRUD operations on some weird virtual computer that you don't understand. And it just goes for pages and pages and pages and pages, where just like every single function you call is a library function. So it's Python, but like, you look at this like, I don't know what it does. Like, I have no idea. You have to understand the full library and all these things. So you lose that the intuitive, like the Python idioms are lost. And like the knowledge you have of Python doesn't really help you with these code bases, which I think is like a smell that we can't express concepts in Python. We're like hitting the limitations of the language. Last example, PyTorch, same thing. If you're trying to create like a handwriting recognition model, this is fine, you create like layers and stuff, but when you hook them together, again, you're like, there's some other language you're calling into that's like an API that you're doing CRUD operations on. This is not a computational graph, this does not look like imperative code, it's like some other kind of weird thing that you have to understand. So it would be great if you could express this kind of natively in Python itself. And if you look at languages like Mojo, they actually do that. The kernel functions themselves are written in Python. You don't have to have all this kind of extra stuff around, which is interesting. Okay, so that's the kind of typing information and expressivity. I was going to say that one of the solutions that is out there is there's a PEP proposal for adding macros into Python to try to solve some of these issues. And the idea is that basically it provides a way to extend the Python language using Python. So think about adding like new keywords to Python or new structures to Python, like a with statement or a match statement or whatever, but you can use Python to do it. It's kind of a like circular reasoning, but there's a proposal to do that. This is the example from the PEP where he creates like a match statement just from scratch, which is really cool. And it expands into this code. I'm not going to go into this, but the point is like it's out there. So people are trying to do this one, which makes me really happy. And I wanted to take it back to kind of the thing that Paul Graham and Peter Norvig talk about a lot, which is like macros. So Python doesn't have macros. That's the one Lisp feature it doesn't have. Macros are like where you write a little bit of code and it expands into some huge other piece of code under the covers. It's not like a function call because it happens at compile time. And so languages before Python used a ton of these. Python famously does not. I think the gist of it is that macros let you write code that matches your brain. Instead of adapting your brain to the code, adapt the code to your brain. That's the general idea of what's possible with macros. There's a lot of examples we have in humanity. Shorthand writing is kind of like a macro, right? If you ever look at Bach's musical notation, if you hear Bach, it's like all kinds of notes, but if you look at the actual written version, it's very short because he made up his own notation, so it's easier for him to understand. Or another analogy for macros is words like schadenfreude, which means something very specific, right? It's like a specific word in a specific language that means a very specific thing. Or saudade in Portuguese, which is like kind of this longing, nostalgic longing. It takes me like a minute to explain what that word means, but if you know the word saudade, it's like very precise about what it is. So those are kind of like macros in human language that we use to be very precise about our intention. And the idea is that what if Python had that ability to provide like precision in our intention? Okay, so now let's talk about the future. So what might Python migrate to next? Well, we already did it. We already did it once. We got to Python 3, right? So congratulations. I never thought we would get here. Honestly, I didn't think it was going to happen. It originally started in April 5th, 2006, and it lasted until April 2020. So it's 14 years. Who remembers the wall of shame? Yeah, so this is like all the packages that hadn't moved to Python 3 yet. This is a snapshot from 5 years after it started. NumPy is not even on the first page. That's how different Python was back then, which is unbelievable to me. You can see Django still red. I think that was one of the last ones to go. But it was really cool because Guido knew it was important to do it. I think what he said at the time is like there'll be more Python programmers in the future than there ever have been up until this point. So let's fix the language so that by the time they get here, it'll be better for them. Like it's planting trees, right? You'll never walk under kind of thing. So super, super cool. And it was really hard. I mean, talk to anyone who raised their hand about the battle scars we all have from this, about not wanting to ever do a migration like that again. Okay, so that happened. But there's a bunch of other potential options. So the Go community, Kubernetes, it's written in Go. Why wasn't it written in Python? That's like our lane, right? What happened there? TypeScript, you see some ports happening there. Rust, people talk about, and then you say people going to like these other dialects of Python or other runtimes. So there's a lot of options. Maybe new languages will emerge that we haven't even thought of yet. And I would say, I'd say like there's traction in all of these areas where they're starting to draw parts of the Python community out. And it's interesting to see kind of like leaks in the community going to these places, and it makes you wonder like why? Why, like if you look at the rough linting tool for Python, why are people doing it? Well, it needs to run fast enough that you can run it like all the time, right? And that's a requirement, and Python just literally can't go that fast. It can't. So let's talk about what the successor to Python needs to be. It might be Python itself. It might be another language. I don't know. Straight line performance, either ahead of time compilation or JIT compilation. Some kind of parallelism, multi-core GPUs, TPUs, has to be like natively supported. Some kind of type system that lets you go fast. And then some kind of macros, some way to express higher level concepts. And I'm going to get into that in a second. And then maybe other features. So this is where I call on the rest of you, like talk to each other, go on the Python ideas lists. If you have things that you know from like subject matter expert domain that you work in, that like, hey, Python's missing this, and if it had this, it would be better for the future, and a lot of people actually need it. Like, that is the most valuable thing, your unique knowledge specific to the domain that you do your work in or your interests. Like, please bring that out, because I think a lot of people don't even know. And the closer, like, I know stuff about writing code, but there's, if you know a lot about biology or something like that, like, that's where the really interesting valued features are. So please bring those up. I think the last feature that is needed here, though, is automated porting. The 2 to 3 transition was crazy hard because we all had to do it manually. There's some tools, but it was hard. And now with AI, in the way that it is, it's kind of, you can imagine like a Python 3 to Python 4 porting tool that's pretty good. Like, like if you look at AI, you're like, here's the test suite, here's the code, bring it across. Like, it's theoretically possible a lot of this could be automated, which is kind of mind-blowing if 4 years ago you would never have thought that. And so that kind of comes to this existential crisis, which is where I'm going to end off, which is, why are we even writing programs anymore? Like, why do we need to code anymore, right? Like, isn't AI just going to do everything for us? Like, do you have that feeling? We have all these models that came out, like generative AI models that came out in December that are really, really good at writing code. It's like shockingly good. And so, you have to wonder, like, do I even need to know how to write code anymore? It's a really scary thought. I see there being 2 camps in this world that I want to talk through. One is that we don't need to know how to write code. If you've read Steve Yegge, he's a former Googler, done a lot of really great work. He has this project called Gastown, named after here in Vancouver, which is kind of like this crazy AI development workflow, I would call it. And he basically sees code as a byproduct, just like assembly language. Like, you run the compiler, it spits out some assembly language, you never look at it, right? It's just the agents and AI are going to do everything. So let's say that's one camp. And the other camp is the readability of the code matters. Like, the humans still matter. Like, we still need to understand the systems, which I think is maybe the Paul Graham 100-year language kind of viewpoint. Okay, those are the kind of the 2 poles I see. The ephemeral camp, it's like they think, like, I'm going to write some human text that's going to describe the software, and software development is going to be more like product management or architecture, which is not disparaging that, just saying what it is. And again, it's just like, I take my C code, I compile it, I take all the rest of the pipeline for granted. I never have to think about it. Maybe some specialists need to know like the details of how to actually write code, but not everybody. The readability camp, on the other hand, like, we need really good abstractions to describe these systems in a very abstract way. And this is what I'm talking about, macros or higher level of principles. Like, we need code, we need to be able to express ourselves as close to the intention of what we're trying to build as possible. And our feeling, let's say in the readability camp, is that human language is never going to be precise enough. There's so much ambiguity. Like, how many times have you been confused with people you work with or people you care about? Ambiguity is like the human condition, right? So I'm just kind of skeptical that human language is going to solve it. And there's another assertion there, which is like, humans ultimately have to be responsible for the systems that are running, and we have to fix it if it's broken. So our ability to understand seems really critical. So I think that's the opportunity ahead. Paul Graham, in that same PyCon keynote that he did, he said this. He said, you can design a language by just writing down the code that you want to write, regardless of whether or not you have a compiler that can actually compile it or a machine to run on. And like to me, this is like the ideal state. Like here's how I want to describe my program with intention, right? I have a friend who does quantum physics simulations, and he's shown me what he would want it to look like, and it's not C++, and it's not Python, it's some other thing. And so I think Paul Graham's vision can be realized. So we'll co-design language extensions with AI. Bottoms up, we'll grow the language to the problem. We'll write really high-level specifications of the code using that. And then AI will optimize for our ability to understand as humans and meet us where we're at with our limitations. And the ephemeral camp can just ignore it, and that's fine. Everybody's happy, right? So that's it. My conclusions again. Can we evolve to seize this opportunity? I think the answer is yes. It's possible. Will we? I don't know. And where will we go next? I don't know. But I do hope this community stays together because I think the people are what make it what it is. And so one way or another, I hope that we all find each other again. So I will see you on the other side of this transition, one way or another. Thanks. Yeah.